Hi everyone, this is Madhav. I'm here with a monster of an integration question. You might be wondering, why am I here with a monster of an integration question? It's because this one, it requires basically everything that I learned in my calculus class in university. So I was like, hey, if I can go back, work on this, then I can basically, be guaranteed that I understand what is going on in calculus. I have zero intention for this to be a beginner-friendly video. This is going to be a monster of a question and a monster of a video. I will explain some basic concepts along the way, but really I won't explain much. Like, you'll find if you don't know what is going on, don't worry. Like, it's not meant to be friendly. Anyways, if you're curious, hey, what does someone do in university level calculus, then prepare yourself for a lot of frustration. So here we have an integral. We could just use a computational method like discretization to solve this, but we're not going to do that because, like, screw it. I don't know, they need something to put on tests, right? Anyways, we're going to try and do this the long way and the hard way and the not fun way with formulas. The first step is we have a big ugly fraction. We don't like it. However, we do notice that the denominator's degree, it's higher than the numerator's degree is higher than the denominator's degree. So because of that, we're going to be trying to simplify this fraction using algebraic long division before we proceed. So I just wrote that out. Here's my algebraic long division. I divide by the polynomial over here. Here's the polynomial being divided over here. I wanted to get x raised to the 4 to multiply by something so that I would get 2x to the 5. So I multiplied by 2x because 2x times x to the 4, that's 2x to the 5 down here. And then all of the other terms got multiplied by 2x as well. When I subtract that away, I get all of these first three terms cancelling out. Yeah. And then I have 1 left over as a remainder. So this big ugly fraction turns into 2x plus 1 over this thingy right here, which is good. So now we took the big ugly fraction and then we simplified it using algebraic long division because we saw that this condition was true. Now, because we have, these two terms in our integral, and this term looks a lot more friendly than this one, we're just going to get this term over by itself. And here we have this integral turned into a slightly more friendly integral. At least we know what the first term is, right? Now, we want to figure out this next part. So we still have a rational integral, right? We still have a fraction that is somewhat ugly. It's less ugly than before, but it's somewhat ugly. In this case, we cannot get this to be any simpler in terms of breaking it into multiple fractions because it's already, just 1 over some denominator. One thing you might notice, though, is that this denominator, we are able to factor it. Because if we let y equals x squared, then this thing just becomes a quadratic. And we know how to factor those with our, grade 10 math knowledge. So we let y equals x squared, and this and that says factor our new expression as y plus 1 squared, and then we put in here, you know, we replace y with x squared again. Now recall that this part was on the bottom, so what we have is this ugly thing. We can factor it into a, you know, a little bit less ugly thing. So now what do we do? Well, what would be nice is we have like this x squared plus 1 thing, right? What would be nice is if we could combine these terms into one, then we would just have one term squared, which would be easier to deal with than, you know, 2 terms squared, which is going to give us like a polynomial, a full polynomial like this. So how can we get this thing down here to be 1 times squared? That's our key question. The way that we're going to approach it is a technique called trigonometric substitution. I don't expect you to know it. So if you haven't heard of it, don't worry. I hadn't heard of it either until recently. Here's the rationale for it. If we have, there's this trigonometric identity, which is kind of the basic one that most people will have heard of. So we have cos squared theta plus sine squared theta equals 1. Yeah, you might have seen this before. Anyone remember where we get this from? Let me show you. So let's say we have a triangle. It's a right triangle with some angle that's theta, and the special thing about this right triangle is it has an hypotenuse of 1. So then I don't know what these other two sides are. I'm just gonna label them x and y because I don't know what they are. They could be any variable. The only side I know is this hypotenuse is 1. So here we see that by the Pythagorean theorem, x squared plus y squared is equal to 1 squared, which is just 1. And what are x and y? Well, if we do cos theta, it's equal to x over 1. Yeah? If we do sine theta, it's equal to y over 1. And so x is equal to cos theta, y is equal to sine theta. So we have cos squared theta plus sine squared theta, it's equal to 1. Cool. So that's part 1. The other thing we're going to do is we're also going to divide everything, both sides of the equation, by cos squared theta. Because we're doing that on both sides, we're not changing anything, right? We can do this. What that gets us is, let's split this up into 2 fractions. Cos squared theta over cos squared theta plus sine squared theta over cos squared theta. And over here, 1 over cos squared theta, I'm just going to write that as its inverse, which is the secant squared. There we are. This cancels out to be 1. Sine squared theta over cos squared theta, just on the side, that's the same thing as sine theta over cos theta all squared. Reason being that the square on a fraction distributes to both the top and the bottom of the fraction. And so sine theta over cos theta, well, we recognize that as tan theta. But we have tan theta squared, so we have tan squared theta here. And that's equal to secant squared theta. this is the identity we need. So let's go back. We're going to be using this identity to form the basis of trigonometric substitution. The key idea, as you might have noticed in that identity, was we had tan squared theta plus 1 equals secant squared theta. That's kind of what we were talking about, right? We wanted to go from these two terms, which look very similar to these two terms. We wanted to convert that into just one term. And hey, what do we have here? Just one term. Okay, that's useful. So that's exactly what we're going to do. We're going to let x equals tan theta, because then we have here tan squared theta. We're just going to take the derivative because we're going to need it soon. So we just take the derivative with respect to theta on both sides. Oops, this should say with respect to theta. So on the left we took the derivative of x with respect to theta, on the right we took the derivative of tan theta with respect to theta. If you don't know what that is, well, we just use what we just used. Tan of theta, it is sine theta over cos theta. And then we just use the quotient rule to take this derivative. You can check my math, I hope you will. It works out that we got secant squared. So this thing, it's equal to secant squared. Anyway, it's just key idea is this and this. We need these. We're going to take x, replace it over here with tan of theta, so that we can go from these two terms to this term right here using this identity. So we have now this integral. The only issue is the differential here, it's in dx, and then this variable is in theta. So this is where this equation comes in handy. We can multiply both sides by d theta and then use that to have this expression right here. Just multiplied both sides by theta. So now where we see a dx, we're just going to write this stuff over here. When I first saw this, I was like, this is black magic. How can you just treat differentials like fractions? If you want to go down the rabbit hole I did of like rage and all that, just search this up. Differentials as fractions, and then you'll hear lots of people yelling about it on the internet. Anyways, when we have this thing here, we achieved our goal. Now we no longer have two terms, we have one term. And so we can even simplify secant squared of theta squared. Well, that's just secant to the 4 theta. We also substitute it in for dx here, right? You can see this secant squared theta up top cancels out with this secant to the 4 theta in the bottom, and finally we have 1 over secant squared theta, take the inverse, 1 over, well, you just have cosine squared of theta with respect to theta. That's what we're taking the integral of. And so we took our ugly fraction, and then we now have a term like this, which is nice. That's the goal of trigonometric substitution. Note also that since x is equal to tan theta, you just take the arctan on both sides. On the right side, it cancels out with, arctan of theta, tan of theta, so you just get theta. On the left side, you have arctan of x. I just noted this because we're going to need this to simplify this little thingy over here. So the way that we're going to simplify this is we need to use trigonometric shenanigans. I think that's the technical term. So to get this, we don't really like the integral of like cosine raised to some power. We don't have many rules for that. We do have rules though for just cosine of something, right? Cosine of something we can deal with. If it's not too complicated, we'll figure it out. So let's go from this to cosine of something instead. We want a trigonometric identity that has both cosine squared theta equal to some other thing, which is just like cosine of something, not cosine squared. If we can get that, then we can take that equation, isolate for cosine squared of theta on one side, and then just have cosine of something on the other side, not squared. The equation we're going to use is this one. So cosine of 2 theta, this is the double angle identity. It's cosine squared theta minus sine squared theta. If you want a proof of this one, well, it depends. Do you know the double, what is this, sum of angle identity? Do you know this one? If you know this one, then cosine of 2 theta is easy, because you just have like cosine theta plus theta is cosine 2 theta, and then this is just the double, sum of angle identities. Anyway, if you don't know this identity, then that's kind of cheating. What you can do is you can go to this page, which I will put in the description, where you can read through this very it's not too long, very geometrically intense proof of the sum of angle identity. There we are. Anyways, I'm gonna carry on here because we have our identity and it's equal to, we derived it in air quotes from the sum of angles identity. So we have our identity. Let's do what I said, get cosine squared of theta on one side and then just cos of something on the other. Well, the first thing is, if we're going to just get cosine squared on one side, then we need to get rid of this sine squared term, and we just substituted for that that identity I just showed you, the one that I derived this from, cosine squared plus sine squared equals 1. So using that, I just replaced the sine squared with this, isolate on one side of the equation. Then I combined my terms like so, and I isolated for cosine squared of theta on one side. So just add 1 on both sides and then divide by 2 on both sides. Here we are. Now we can take this and substitute that in here. So we take this, put it in here. I just broke up the fraction, into 2 parts, because that lets me break it up into 2 integrals, where I just factored out this 1/2 of the integral. This part is easy, we know how to get that. This part's kinda not so easy. What we'll have to do is we kinda have to guess and check. Here is the number one thing, like especially if in your university setting, I hate how they make you memorize so much stuff without like actually looking at the proofs. Why is this thing the way it is? If you're ever in that panic mode situation where you just can't come up with like, what is going on? How do I integrate this? I don't remember the formulas, they make me regurgitate. Remember that what you need to keep in mind is integration is the opposite of differentiation. So if you're taking the derivative of something, right? Look, so let's say I want to get like the integral of cosine of 2 theta. Well, if I take the derivative of something and it leads to cosine of 2 theta, yeah, then if I integrate on both sides, on the left side I just cancel out the derivative, and on the right side if I write the integral, well, that's what I'm looking for. What I'm saying is this is going to be equal to whatever you can differentiate to get cosine of 2 theta. Yeah? So figure out something you can differentiate which gives you cosine of 2 theta, and that will be related to the final integral formula you're looking for. Here's a simple example. So I assume you know that the integral of cos theta, just cos theta alone, it's sine theta plus c for some constant c, right? Some real number c. Well, the reason that's true is because and this is a circular definition, obviously, like if you don't know why the derivative is the way it is, then there's no point. But if you do know why it is the way it is, then if you take the derivative of sine theta plus c, what do you get? You get cos theta. So if you just remember this part, the differentiation part of formula, and more importantly, if you understand this part, why is it the way it is, and this one you need to look at Desmos and like graphically understand it for this particular formula, then you automatically know the integration formula. And so in a similar spirit, what I did was I noted that the derivative of this here, it's equal to cosine of 2 theta, and you can work that out by yourself. Therefore, the integral must be this. And thus, finally, using the sine identity, the double angle identity to simplify this part, we have our final result. This integral is just equal to this. Obviously, these are going to cancel out. Now I have this result. I have basically all the parts I need, because if you remember, this cosine squared theta is just equal to this derivative, this integral. This integral is simply one part of the big integral, and the big integral is related to the original. So if I just substitute backwards, fulfill the entire chain, I should be good to go. So in the home stretch of this monstrous question now, let's just put everything together. 8 pages, 9 pages of stuff later, we have to substitute backwards 4 into 3 into 2 into 1. I was numbering my equations as I went. This is let me just put the original question at the start. Here's the original question we were given. We turned that into this by simplifying with algebraic long division, which we turned into this by factoring, which we turned into this by trigonometric substitution. We solved the trigonometric substitution integral using identities, and then now we can just integrate this with the power rule. Here we found the answer already of this thing. Here, power rule, and just take a constant at the end, because it could be shifted up and down by anything. This cos theta, sine theta thing, we want to simplify this. We don't want to just leave that in our answer. So if you recall earlier, the substitution I used was x equals tan theta, explained why. Theta is thus the arctan of x. So when we substitute that for theta, we get this ugly looking thing. We'd like to simplify that a bit, because this looks ugly, and we can use a little drawing for that. So note I made this right triangle. It has an angle here of theta. And what we know about this triangle is that tan theta is equal to x. And so that's what I did. I did tan theta, opposite over adjacent, is equal to x over 1, or x. So if that is x over 1, this is a right triangle, then by the Pythagorean theorem, this is x squared plus 1, take the square root, right? This side, this hypotenuse length. And now that we figured that out, well, we know what these cos theta, sin theta terms should be. Because now we've specified the triangle enough so that we just know cos theta is adjacent over hypotenuse, 1 over this business right here. Sin theta is opposite over hypotenuse, x over this business right here. So it would have been hard to calculate what the hypotenuse was and then like geometry in our head. That's why I drew it out. And so we can just take this expression for cos theta, put it up here, for sin theta, and put it up here. And what we get is, well, we have the x squared that we did originally, right here. Then we have 1/2. I just wrote it as like, part of it's 1/2. Blended that into the fraction. Since we have cos theta and sin theta being multiplied together here, then these two square root of x squared plus 1 terms on the bottom, they multiply together so that we just have x squared plus 1. The square roots cancel out. And we also have an x over here on the denominator from sin theta. Yeah? We have 1/2 theta, which I just left as arctan of x. And finally our constant c. So here, after 9 pages of work, is what we were looking for with the big ugly mess. I don't think that this is terribly insightful in terms of like teaching you understanding of math, especially not the way they teach at university, which is just memorize like every formula along the way and then plug and chug. However, it is interesting at least to note just how much effort mathematicians are willing to go through to like go from one step to the other step to the other step to the other step, just so that they can take an integral that's written in a way they don't like and transform it into an integral or a series of integrals that they do like. It's kind of weird. Mathematicians are odd people. Anyways, if I had this, I would never do this. I would just write a program that could, do the strategy that I mentioned at the beginning, discretization, and I'll link to a video on that, which is a much more fun video for me because I just was playing around with Desmos. If you're interested. Bye.